Let's look at the seventh step of solving linear programming problems using Simplex method. The seventh step is to repeat steps 5 and 6. Now in the previous step, that is step number 6, we obtained this improved solution. However, we don't know whether this is the optimal solution or not. So first we will perform the optimality test on this solution. Now in order to perform the optimality test, as we have seen in step number 5, we have to find the values of zj and cj minus zj. Now elements in the zj row represent the decrease in the value of the objective function or profit, which will result if one unit of the variable in the jth column is brought into the product mix. So we have already seen what this means in detail in step number 5. Now in this step we will simply calculate the value of zj for each of these columns, and the way to calculate is first multiply the cb value with the corresponding value in the jth column and then add all those products that we obtained. So 0 multiplied by 0 is 0 and 10 multiplied by 1 is 10. So 10 plus 0 is 10. Similarly for x2, 0 multiplied by 5 is 0 and 10 multiplied by 1 by 4 is 5 by 2. So 0 plus 5 by 2 is 5 by 2. So let's note that down. 0 multiplied by 1 is 0. 10 multiplied by 0 is 0. So 0 plus 0 is 0. 0 multiplied by minus 1 by 2 is 0. And 10 multiplied by 1 by 40 is 1 by 4. So this becomes 1 by 4. For column B, 0 into 400 is 0. And 10 multiplied by 40 is 400. So 0 plus 400 is 400. Next we have to calculate the value of cj minus zj for each of these columns. This row is also known as the net evaluation row and is obtained by subtracting column wise the value of zj from the cj values. So as you can note that cj is the profit per unit if one unit of that variable is added into the product mix, and zj represents the loss in profit if that one unit is added in the product mix. So if we subtract zj from cj, we'll get the net profit value. So let's calculate the value. So 10 minus 10 is 0. 4 minus 5 by 2. So 4 minus 5 by 2. So 2 is the LCM. This is 1. So this becomes 8 minus 5. So this is 3 by 2. So this is 3 by 2. 0 minus 0 is 0. 0 minus 1 by 4 is minus 1 by 4. So just as a note, at this point, this value of 400 here is the profit for this solution. So now we have already found out the value of cj minus zj. Now we'll use the values in this row to determine whether or not the current solution is optimal. So any positive value in the cj minus zj row indicates the amount by which the profit will be increased if a unit of that corresponding variable is introduced into the solution, whereas a negative value indicates the amount by which the profit will be decreased if a unit of the corresponding variable is introduced in the solution. So the optimality test says that in case all the values are negative or 0, the current solution is optimal. However, if any element is positive, then the solution is not optimal and there is scope for further improvement. So here we can see that this value here for column x2 is positive. So what this means is that there is scope for further improvement in this solution. So now let's move to the step number 6, where we will iterate towards the optimal solution. So in order to iterate towards the optimal solution, we have to observe the values of Cj minus Zj for different columns and mark the column for the maximum positive value. So here, this column here 3 by 2, which is within x2, is the maximum positive value. So basically this becomes your entering variable. Which means that this product should be introduced in the product mix because it is going to give us more profits. So this column becomes your key column. Now again, if we had two columns with the same value of Cj minus Zj, that means if we had a tie, then we can select any one of those. So here we have found out the entering variable, but now we need to find the departing variable. So we have one variable which is entering, or one product which is entering, and one which is coming out of the product mix. So in order to do that, we have to find the replacement ratio, which is represented by theta. This ratio indicates the number of units of a variable that can be produced by trading all of the current level of basic variables. And we have already looked at the detailed explanation of what these values mean in step number 6. So the way to find these values is to divide the value in column B with the corresponding values in the column x2, that is the key column. So here 400 divided by 5, which is 80, and 40 divided by 1 by 4. So 40 divided by 1 by 4, this will become 40 multiplied by 4, which is equal to 160. The next step is to mark the row containing the minimum non-negative ratio. 0 is also considered as non-negative. So which is the minimum? This is the minimum, 80. So this becomes our key row. So we have a key column and we have a key row. So the key column represents the column of the variable which is going to be entering the solution, while the key row represents the row of the variable which is going to be departing the solution. So this value here, S1, is the departing variable. Now the element which lies at the intersection of the key column and key row is known as the key element. So in our case 5 is the key element, so we'll enclose this in parenthesis to indicate the key element. So now that we have identified the entering variable and the departing variable, we need to create a revised simplex table providing an improved solution. So the first step is that the incoming variable now replaces the departing variable, and the coefficient of the incoming variable in the objective function is entered in the CB column. So let's do that. So in the basis column, now we place x2, and the coefficient of x2 in the objective function is 4. So 4 comes in the CB column. Now next, since x2 is the solution or being added to the product mix, basically this column should have ones and zeros. So we have to make this key element as 1. So what we'll do is we'll divide all of these elements by 5. So basically what we are doing is that we are making this key element as 1. So 0 divided by 5 will be 0, 5 divided by 5 will be 1, 1 divided by 5 will be 1 by 5, minus 1 by 2 divided by 5 will be minus 1 by 10, and 400 divided by 5 will be 80. So let me replace these numbers. So 0, 1, 1 by 5, minus 1 by 10, and 80. Now each remaining row of the matrix is substituted by a new row called replaced row. And how do we do that? So first, the variable, that is in this case we have x1, and its contribution, that is the corresponding value in the CB column, are reproduced as it is without any change. Now all the remaining elements are replaced by new elements, and the idea is that now this element in the key column has to be made 0 by multiplying something like a multiple to this key element, which is 1, and then subtracting from the element in the row which is being replaced. So let's see what will be that multiple. That multiple is the key. So what we have to do is 1 by 4, this is the value in the row which is being replaced, minus 1, which is the current key element, multiplied by x is equal to 0. Right? So we have to multiply the key element with a multiple and subtract it from this value 1 by 4 such that this value becomes 0. So let's solve this for x. So or 1 by 4 minus 1 x equals to 0, or let's take x on the other side, x is equal to 1 by 4. So the multiple is 1 by 4. Now since we are doing this for the key column, we have to do the same for all the other columns. So basically what we are doing is we are taking the key row element, so 0, multiply it by the multiple that we found, and this thing we have to subtract from the corresponding element in that column for the row which is being replaced, that is 1. So 1 minus this, so this becomes 0, so this is 1. So for the first column 1 is the new value, for the second column this becomes 0. So let me do that. In the meantime, what I'll do is I'll also remove the zj and cj minus zj values, because we'll have to calculate it again for the new improved solution. So this value now becomes 0. Same thing here. So what we have to do is 0 minus 1 by 5 into 1 by 4. So this becomes 5 4s are 20, so minus 1 by 20. So this is minus 1 by 20. Right now I'm writing it here, I'll later on remove these values and replace it with the new values. For column S2, 1 by 40 minus 1 by 10 into 1 by 4. So 1 by 40 minus into minus is plus, and 1 by 10 into 4 is 40. So this is equal to 2 by 40, which is equal to 1 by 20. So this value is 1 by 20. For column B, again the same thing. So 40 minus 80 multiplied by 1 by 4. So 4 2s are 8 and 0. So 40 minus 20, which is equal to 20. So this value is 20. So let me now replace these new values for this row. So I've replaced these values in x1 row. So this is our new improved solution. Now again, let's find the values of zj and cj minus zj to find out if this is an optimal solution or not. So 4 multiplied by 0 is 0, plus 10 multiplied by 1 is 10. 4 multiplied by 1 is 4. 10 multiplied by 0 is 0. 4 multiplied by 1 by 5 is 4 by 5, plus 10 multiplied by minus 1 by 20. So 10 multiplied by minus 1 by 20. So this is 2, this is 1. So 4 by 5, and this becomes plus minus 1 by 2. So 5 2s are 10, 2 multiplied by 4 is 8, minus 2 5s are 10, 5 multiplied by 1 is 5, 3 by 10. So this is 3 by 10. Now again 4 multiplied by minus 1 by 10, so minus 4 by 10, plus 10 multiplied by 1 by 20, so this becomes 1 by 2. LCM is 10 minus 4 plus 5, 1 by 10. So this becomes 1 by 10. Now 4 multiplied by 80 is 320. 10 multiplied by 20 is 200. So this becomes 520. Now let's find the value of Cj minus Zj. So 10 minus 10 is 0. 4 minus 4 is 0. 0 minus 3 by 10 is minus 3 by 10. 0 minus 1 by 10 is minus 1 by 10. So here all the values are either 0 or negative. So what that means is that this is the optimal solution. So now what is the solution? So the solution is that x1 is equal to 20 and x2 is equal to 80. So x1 equals to 20, x2 equals to 80, and the value of p, that is the objective function, is 520. Actually, let's calculate that. So we'll substitute these values in the objective function. So 10 multiplied by x1, which is 20, so 10 multiplied by 20, plus 4 multiplied by x2, so 4 multiplied by 80. And for S1 and S2, irrespective of their values, since the coefficient is 0, this whole thing becomes 0. Now actually, if you look at this step that we had done, we multiplied 4 with 80, that is this, and we multiplied 10 with 20, which is this. And that is how we had obtained the value 520. So let's do it again. So this is 200 plus 8 4s are 32, so 320, this becomes 520. Also, since the slack variables are not appearing in this solution in the basis column, So the unused capacity is 0. Actually, let's validate that by putting these values of x1 and x2 in these constraints. So let's take the first constraint, 20 multiplied by x1. 20 multiplied by x1 is 20 multiplied by 20, which is 400, plus 10 multiplied by 80, which is 800. So this itself becomes 1200, which is the maximum capacity of the blanking shop. Now the second constraint, 40 multiplied by x1, so 40 multiplied by 20, which is 800, plus 10 multiplied by 80, which is 800. This becomes 1600, and that is the maximum capacity of the gear shop. So here also there is no unused capacity. So this is how we obtain the solution for a linear programming problem using the simplex method. Now, even though the name is simplex method, I don't find anything simple about this method. Probably this is the most complex method in operation research. So maybe the name should have been complex method. Anyways, I hope we have been able to make the steps easy to understand, and with practice you will be able to master this method.